my talk today, I'm going to push the envelope this morning because it's the last day of the conference and it's time to think forward, not backwards. And so my talk is entitled Changes Towards a Digital Transformation to Infinity and Beyond. And I'm going to start with the fourth industrial revolution, which has probably been mentioned a half a dozen times or so at this conference this week, so I'll keep it brief. You know, we started the agricultural age, where the people who were successful are people who can do, and mechanization. And when we went to the industrial age, we began to mechanize, and it became people who can get people to do things. And then we moved to the electrical age around the turn of the last century, and it became, how can we leverage what we have? How can we automate? How can we mechanize? How can we automate things with electricity? And then we went to the digital age, and the question became, how do we automate things with computers? And now we're entering the next revolution. This is the age of imagination, if you want to call it. And the question is no longer how can we use computers, but how can we use our imagination, and how can we think outside the box to make things better. Someone mentioned a Star Trek Next Generation scene where the chief engineer says, computer, check the tachyon, blah, 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 and the computer was able to do it. And the question is, how do we get there? And the comment I have is we're kind of almost there from a technology standpoint. The technology always precedes the practicality, which always precedes the oil and gas industry, which is always 30 years behind. Because I can go to DALL-E. DALL-E is an artificial intelligence image generator. This is not a search engine, this is an image generator. And I could literally put in 2 chickens riding a motorcycle over a bridge in the style of stuffed animals, and within 30 seconds I get that picture on the right. Generated, not searched. Or a pink elephant sitting on a refrigerator in the style of a New Yorker cartoon. Generated. Boom. So here's my question. If we can literally take natural language processing and convert that to a bunch of parameters, which then can convert to an image, a photorealistic image of 2 chickens riding a motorcycle that look like stuffed animals driving across a bridge, why can't we apply that to our industry? Why can't we apply that to automation? And so I'm going to show a picture that's familiar to a lot of people in this room. This is a gas processing facility, and I want you to try to take what I just said about DALL-E and apply it to the thought here, okay? So let's simplify this image. You have a wellhead, and then you have a pathway all the way to, say, the sales pipeline or to your stovetop, if you will. And there's a host of pieces of equipment between the beginning and the end. And this is our product right here. The third one in is this is our product in green here. There it is. And I'll get to the story that we've made our unit smart, and I'll talk a little bit about what we do in a second. But for now, take my word, and we've made this unit smart. But what would happen if we went through this entire gas processing facility and made everything smart? And we'll define smart in a minute, but go with it for now. And then we took a hyperbrain and we made them all communicate to each other. So you would have a machine learning gas processing facility. You don't longer have smart pieces of equipment. This is a smart facility. So this is IIoT brought up to the next level. Well, I'm going to show you we've done this to our unit, and Mary May's made it smart, and nothing along that system can't be made the same magic we've done to our units, and nothing there is beyond the realm of modern technology. However, how many people here have a fully functional, smart, self-automated gas processing facility? I think we represent probably all the super majors in this room. We'll all say no. And imagine this, right? So you have sensors at the wellhead that detect a problem, and before it even makes it to the glycol dehy unit, it's already changing its flow rate, it's already changing its temperature to adjust for the problem that happened 30 minutes in advance. Because the wellhead knows that there's suddenly an influx of water, or the temperature suddenly dropped, or the gas flow rate changed, or the liquid water cuts changed. Any of those factors could come into play, and the amine plant can adjust its flow rate. Or it adds defoamer because I know something's going to go wrong. All of these things can actually be talking to each other and preempting the issues, solving the problems, minimizing the issues. Not to mention the bread and butter stuff like preventative maintenance or twinning, digital twinning, where things are being simulated and optimized. I'm talking about just basic, plain old communications between the units. So imagine being able to say, I want to maintain my system, maintain liquid in a vessel or in a tank at all times without spilling, and that's my process control command. That's what I tell the computer, and the computer figures it out. Or keep the reaction rate at equilibrium, or run it under optimal conditions. Those are all process statements that every process engineer wishes that could be the statement that they want to make to a computer, but then they spend the better part of 6 months converting those statements into very detailed statements that can get converted by a programmer into a code, which then gets converted by an integrator into a PLC. So there's a lot of steps when really this, in theory, might be able to be done relatively soon with verbal natural language. And the reason why is because process designs are driven by the mechanical engineer, right? We build something, the mechanical engineer or the process engineer draws something out, and the process control engineer doesn't come in until after the P&IDs are made. So, and my company is no exception to that. The process control engineer comes in after everything's been designed, and so they're not involved in the process. Process control should be brought up earlier in the system. And so what happens? We just have a list of interlocks, PID loops, and there's few industries that have things like model predictive control or AI, few processes, and that's where we've headed to, but very few processes have done that, and it's not that hard. And then, automation, what's automation for most people here? It's sequencer steps. It's do this, do this, do this, do this, do this, do this in order, and that's it. And the reason why is it's what I call a programming problem. And the technology is there, but it's a programming problem. And I'm going to distinguish those three, what a programming problem is next. There's three different approaches to technology, three different generations, so to speak. The first is programming problems. So if any of you remember the X80 modules from Radio Shack in the 1980s, you were able to turn your lights on and off with a box like that on the wall there. And if you were good, you could wire up. And if you got, they had plug-in modules, they had a light switch. But if you wanted to do anything like turn the light on at 6 p.m., you needed a computer, you needed to program in Visual Basic, Basic, and send the commands to that box, and that box would then communicate. And it was really cool. It was home automation, but it was only accessible to people who knew how to program in BASIC and knew how to set this up. And then we move forward 15, 20 years, and most of us have Alexas or Siris in our homes, and now you plug it in, and the light switch is automatically configured for you, or you configure the light switch. You have to tell it which light switch you want it to control, but it's pretty straightforward and accessible to most of us. But my grandmother still can't do it because she doesn't really know that box can be controlled by that Siri, or is it that Siri? There's still, it's a configuration problem. It's not a programming problem. But the last step is auto configuration. That's the last phase of this project. That's where you literally plug in some lights, put some light bulbs in, and Siri or Alexa will automatically figure out what those lights are, where they belong, and exactly what needs to be done. And you never have to say, turn on living room light 3. It just says, Alexa, turn on the light. It knows which room you're in. It guesses which light you want on, and there we go. We're not there yet at home automation. We're in the middle phase. So, quick plug about my company, because I have to get paid. We are a startup company, started in 2016. We're a growth phase company. We took a technology that was actually developed in the 1930s and re-commercialized in the 1980s and 90s. You may have heard of it as sulfurox or low-cat. We've taken a chemical reaction that converts hydrogen sulfide to elemental sulfur. So hydrogen sulfide's a gas that appears in about 40% of all natural gas wells, all oil, 40% of all oil wells, and about 100% of all biogas and renewable natural gas sources. And we've developed a process that converts hydrogen sulfide with air, and we create elemental sulfur, which can be used as fertilizer, and water. So we take a toxic gas that's toxic to 1 part per thousand, one breath will kill you, and we convert it to fertilizer. And that's really cool, right? So we're taking a bad thing, we're making it good. We've done this with, it's a liquid chemical reaction. I'll cut to the chase, and the process looks like that. You don't need to know it, there's no test at the end, but I am literally doing one chemical reaction in this phase, one chemical reaction in that phase, and then a solids removal system. So I have 3 important processes to maintain in order to make this system economic. And in the old days, this plant had to be roughly half the size of, 4 times the size of this room, because it was only useful when you had a human being sitting there at the wheel, because the gas flow rate changes, the H2S levels change, and someone's got to sit there and maintain chemical balance and maintain it. So what we've done is we've automated it. And that allowed us to build these units smaller and smaller and smaller and make them economical at smaller and smaller scales. And we made the awful mistake of our first 2 engineers we hired. One was a mechatronics major from Georgia Tech, and the other was a PhD process control engineer from Ohio State. Neither one of them knew what was reasonable or practical, and so when we said automate it, they automated it completely. It's a good mistake to make. So I'll give an example of one of our units. This is a Valkyrie we call our units Valkyries in Pecos, Texas. I've used this one before. It's 3 amine plants and 3 tail gas treaters. So we're taking out H2S and CO2. Coming out of this is a CO2 tailpipe. Typical amine plant requires a half an FTE, plus our units, our old scale units, are about a half to 1 FTE per unit. So that means you need between 1.5 and 1 to 1.5 FTEs per unit. We had 6 units on site, 3 units total. There were 3 of these identical. So you're talking 6 to 8 FTEs is on paper what you need. And then you need a maintenance team, you need a support team, you need a SCADA team, you need data, you need all these other things. And the mission was to do this with 3 FTEs, equivalent, and keep our minimum. Well, we kind of beat that. So we took the amine plant, we added some intelligence to it, we added what we've done to our own systems, which is automate, keeping track of the chemistry, keeping track of the levels, adding extra sensors, adding extra control elements, making those cascading PID loops, making the model predictive control, which was fairly easy with an amine plant. And we were actually able to optimize our amine plant and reduce that. And then on our Valkyrie system, we already do this. We've already understand the chemistry. We put probes in. We put the process in, so we can actually maintain that chemical equilibrium in real time. And we got it down to 1.5 FTEs now. It's about, I put 2 there, but now it's 3 guys who work over a course of 2-week shifts. So about 1.5 FTEs total for these all 6 plants. It's monitored by our control room in San Antonio. They can operate the unit completely. There's no complete remote operations. You don't even need a human on site. The human is just there to check, to make sure nothing's spilling, to change the paper on the filter, and to just, make sure nothing's blowing up. We have about a 99.5% uptime, and the connectivity there is abysmal. Your cell phone gets 2 bars if you stand in the right spot. If you stand in the wrong spot, you get 0 bars. We manage this all through cellular connectivity. So we have low bandwidth, and we're still able to do this. So how did we do this? Let's get to the meat of this story. We model the brain. The human brain has 4 parts to it. It's called the triune brain, even though there's 4 parts. Your amygdala, which is the oldest part of your brain, your fish brain, your reptilian brain, your mammalian brain, and your human brain. And if you kind of think about process control and controls, your fish brain is the simplest part. That's your ESD buttons. Your reptilian brain is the part of the brain that never messes up, that never shuts down, never goes to sleep. That's your PLC. Your mammalian brain is your edge computer, and I'll talk about the edge computer, and then finally your cloud, your Watsons and whatnot, is your human brain. So now, if you think about that, and your brain operates just like this, right? So different sections are doing different things, and when you sleep, your neocortex sleeps, but your reptilian brain doesn't. So if you sever the connection in the cloud, there's no problem. It's like you're going to sleep. Your body still breathes. Your heart still goes. If you sever the connection between your limbic system and your reptilian brain, there's some problems, but honestly, it still runs. And if your reptilian brain should shut down, your heart will still beat. So ultimately, the system will not stop running as long as you get simpler things that are more mission critical. So the higher the processing speed, the longer the data acquisition time, you go up to the right, the slower, the faster response time required, and the higher bandwidth you need, it goes down to the left. And so I'm going to kind of lay this out using the right tool for the job, brain versus brawn. Put your brains where they belong and put the brawn where it needs to be. And I'm going to graph this out graphically quickly. If I look at the computational requirements for a given calculation, and I look at how much data I need to make that calculation, and I start laying out on a map how much information I need. An ESD requires one value, it's an interlock, and requires instant response time. At the other end of the thing is machine learning, where I need a huge amount of data and a huge amount of computational power, and it's going to take some time. And you're already thinking that's the cloud, that's your interlocks, that's your ESD. And then we start throwing other things in. Soft sensors, which can be done at the edge, right? It requires a fair amount of computation, but not a lot of data. Inventory management actually requires a lot of data, but not a lot of computational time. So you could start laying these things out and then taking technology and overlaying on top of this. So now I start putting patches around here, and your PLC is there. I put some fog instruments on the left. Your edge computer is down on the right. There's your AI server on the top right, and then things like your enterprise management systems on the top left. Now, I've laid out all these pieces. Let's connect the dots. So I put APIs where they need to go. You have OPC servers. You make APIs. You put all kinds of things, like let's say a weather app. You will need third party. You pull those in. All those things are connected through different connections. So now that we have this graph, let's rearrange the circles and put this in a way that makes more sense. You could see where I'm getting. I just took all of those things and just redraw them in a little clearer way. And so the center of the system, the most important choice to make, is actually your edge system, because this is going to be the center point of everything. This is going to be the one touching your SCADA system and all these other pieces and your cloud and all these pieces. And so this is the important decision to make. And so we've actually gone with Stratus. I think it's worth mentioning. And I'll explain why in a second. But this layout is actually the way we do things in our system. Is our Stratus, the Stratus computer is a center point of our unit, because it really is important to pick the right center computer. And that's where I'm going to get to in a second of where we're going. And the reason why is because there's three reasons, really, why we chose the Stratus product. And number one is because it's got a very high uptime. It's a very robust piece of equipment that's Class 1 Div 2. And the virtual machining. So we've actually virtual machined our units. They're running 3 virtual machines. I'll get to that. One is Ignition. One is a PostgreSQL database. And one is Windows running Studio 5000 and all the other goodies associated with Windows. So that has allowed us to remote into our system. We're cyber secure with AppGate. And we have Starlink as our modem. So we're using Starlink to get into our unit. We can, if we need to get to the PLC, we open up the Windows box and we can open up Studio 5000 and we can get straight to the PLC. If we need to operate the unit, the operators go to Ignition. And for disaster recovery, we take the database from PostgreSQL, we clone it to the cloud, and if we have a disaster, we can recover by just replacing that database, because the Ignition virtual machine and the Windows virtual machines are just clones of the basic copy. And so that has allowed us to kind of flexibly recreate our units very quickly and very functionally. And then the other thing we've done is we've actually data hogs. We love data. We're an ignition house. So we pull in as much data as we want, including information about the system itself. So Stratus is an OPC UA server. We pull that data in and we historize our memory and CPU usage. We constantly ping our servers and we monitor the ping rate and the latency in real time that then we can then plot later on. So if we have an issue, we could see if was the problem a network issue, was it a memory issue, was it an operational issue? And so that gives us this flexibility because we love data, we love gathering data, and so we gather all that data locally, and our units are hosting all of this data. Interesting comment to make, which is worth mentioning. Because we used to have, about 3 years ago, we had about 3 units. We now have 45 units operating across, 35 units operating across West Texas, New Mexico, California, and Illinois. We sometimes sell our units, we sometimes lease our units, and we sometimes operate about 90% of them. There's only about 3 or 4 we don't operate. So we needed to have a flexible platform, and so Ignition, every system in this, every one of our units operates as an independent SCADA system. This is not a hub and spoke where we control from the cloud like it's 16 widgets in a factory. We have 32 factories. Every one is a standalone SCADA system. And so now each unit has to be its own independent system, which is why we needed a very beefy computer for each unit because it is the SCADA system. And then we need to get that data up to the top, to the cloud, to be able to do analytics. So we went with Starlink. Starlink is beautiful. That's our HMI. Starlink is not very exciting to look at in the field because it's just a dish that doesn't really look like anything. But we have gotten incredible results with Starlink, and we now about have 10 of our 30 units running on Starlink. So let's wrap things up and talk about where we're going. So we went from the electrical age of how do you profit from electricity to how do you profit from data, and now it's how do you profit from innovation. And so that's one of the first footprints of humans recorded, and that's probably one of the most famous footprints in humankind. So how do we go forward? And here's the next step. So we start with data at the instrument level. Everybody has this. This is great. And where I'm going to get to is at the top of the list at the CEO's office. But we take the data and we build an HMI. Okay, we've done this. You guys have all done this. Nothing exciting. We take that data, we take that HMI, and we start building, there we go. Oops, sorry. Metadata, so something an engineer can consume. That's a little bit higher up, right? So we've reduced that HMI to a nugget of information. So our units are operated by exception. They're not operated by somebody controlling things. So we start creating our exceptions. Then we go to the next level. That's our control room, by the way. That's about 27 units being operated. We're up to 32. And then we create our exception global dashboard, and we monitor all 27 units, or 32 units now, remotely by exception, and we're doing that. So now we're up to the top of operations. But we're not done yet, because we could still have data to go. And if you'll notice, there's going to be a jump here from Ignition to Excel. And this is the jump that everybody struggles with. And this is going to be our next goal. And this is what we're working on. Because now we take all that data. We have 20 some odd units running. Now it's 32 running simultaneously. We have 30 KPIs for every one of these units. This is the engineering document. The engineer looks at this and says, okay, this unit's running well, that one's not, make these changes and come back. We jump to the engineer level. But we can keep going because now we can get to the executive level and take that data in a real-time P&L. So we're literally taking the same data and bringing it up and bringing in more, aggregating more, making bigger decisions, and now we get to a real-time P&L. And there's no reason why any of this can't be automated, and I tell you, we're about 2 months away from automating even up to this level. So when you do that, and you take what I talked about at the beginning, you get from granular to strategic, that whole range. And that's how you transform from multiple units to aggregating your data, to corporate success. We went from 3 units to 32 in 3 years. We've done pretty well for ourselves. And let me go back to the beginning. If we're trying to make something smart, we take a phrase and we add that to a process. Well, we could do that at the instrument level. We've all done that. Now we want to make this unit run optimally, like I described at the beginning. But now we go to the control room level, the I engineer, so to speak. We go from IIoT to I operator to I engineer. Minimize operation time. Now we go to the next level, the I executive. Maximize profits. And then finally, if you take all of that data and you put that through a machine learning thing, my boss loves this one, an I CEO, have the computer run the company. Yes, it's fantastic, it's a bit much, but it's worth, it's provocative. Tell a computer to run the company, all the way at the top of the level. So that's where I leave you with thinking about automation all the way from instrumentation all the way up to operations level and executive level. So with that, I thank you for your time. If you have any questions, we'll get it at the